Welcome to lesson 9.5, Apply Compositions of Transformations. So the kind of main idea of this lesson will come down to performing and describing combinations of two or more transformations. And mainly we've looked at reflections, rotations, and slides or glides, which could also be called a translation. So, first thing to look at, a translation followed by a reflection. So, if we look at segment PQ here, it's translated or slid up to P prime, Q prime, and then reflected over line K or about line K to give us segment P double prime, Q double prime. So, paragraph describing that. So, if we have a translation followed by a reflection, they can be performed one after another, and that result is what's known as a glide reflection. So, a translation can also be called a glide, and a glide reflection is a transformation in which every point P is mapped to a point P double prime by the following steps. So again, first we have that translation where PQ becomes P prime Q prime. Then the reflection P prime Q prime becomes P double prime Q double prime. So we go through the steps here, P to P prime, then to final point P double prime. So let's look at a composition of reflections. In compositions, again, you can just think of as two or more, or not composition or reflection, sorry, compositions of transformations, but compositions you can think of as two or more transformations. So it could be a rotation and a rotation, it could be a glide and a glide, could be a reflection, etc. So the vertices of triangle ABC are given at 3, 2, 6, 3, and 7, 1. So first, just graph triangle ABC at those three coordinates and connect them. So A here, B, and C. So that's our original pre-image. They want us to find the final image of triangle ABC after the following glide reflection. So you'll see here I changed our translation from xy becoming x minus 12y to x minus 6y, simply so it would fit on our graph. So the first part of our glide reflection is to take coordinates xy and perform the translation x minus 6 comma y, simply meaning we're going left 6 and up or down 0. So that tells me A prime is at a negative 3, 2, B prime is at 0, 3, and C prime is at 1, 1. So it simply shifted our original pre-image 6 units left. And then the second part of our glide reflection is to reflect in the x-axis, or reflect about or over the x-axis. So I'm going to take A prime, B prime, C prime, reflect them over the x-axis to give A double prime, B double prime, C double prime at the coordinates negative 3, negative 2, 0, negative 3, and 1, negative 1. Then we plot our coordinates and connect them to get our final image. So that final image would be triangle A double prime, B double prime, C double prime. Then another practice of that process. In this case, we're dealing with a composition of transformations with the segment RS. And RS's original coordinates are at 1, negative 3, and 2, negative 6. So plot that one first, our original segment, RS. Then they want us to graph the final image after the following composition. So our composition is a reflection in the y-axis, followed by a rotation of 90 degrees about the origin, which would be 0.00. So first, let's do the reflection. So we're taking RS, reflecting it over the y-axis. So our points would be R prime at -1, -3, and S prime at -2, -6. So there would be R prime, S prime segment. Then we need to rotate that 90 degrees about the origin. So we're taking R prime and S prime, following the rules of rotation about the origin, which would mean we flip our coordinates, and what was our original y coordinate now is x, and we change the sign, and our original x coordinates move to our y coordinates and keep the same sign. So r double prime is at 3, -1, and s double prime is at 6, -2. So rotated 90 degrees, resulting in our final segment image, r double prime, s double prime, right here. So the idea of compositions, when two or more transformations are combined and they form a single transformation, that result is known as a composition of transformations. A glide reflection is an example of those. In this lesson, composition of transformations is only using isometries. So the final preimage is congruent, or the final image is congruent to the original preimage. So if our composition of transformations is only using isometries, our final image is congruent to the preimage. And remember, our isometries would include our rotations, our reflections, and our translations or glides. So our composition theorem, 9.4, simply states the composition of two or more isometries results in an isometry. Pretty simple. Then we also have theorem 9.5, which has to deal with one of these compositions, which is dealing with the composition of reflections in parallel lines or over parallel lines. So simply put, what we can think of is when we're reflecting, followed by another reflection, and it's over two lines that are parallel, it results in a translation, or simply resulting in what could be a slide or a glide of the original to the final. So the theorem reads, if lines K and M are parallel, then a reflection in line K, followed by a reflection in line M, is the same as a translation. So if we look at that, if QP was our original, and we reflected over K, and then reflected that over M, it would result in a final image that would also be the same process as taking segment QP and translating it to the right, in this case. But then we have a couple rules to go with this theorem. So if P double prime is that final image of our original P, then the segment P to P double prime is perpendicular to those lines of reflection K and M, and the distance from P to P double prime is 2 times the distance between our parallel lines K and M. So if the distance between K and M was 7, then the distance from our original point P to P double prime would be twice that, or 14. So then we get to example 2 here, which says, in the diagram, a reflection in line K maps segment GH to G prime H prime. A reflection in line M maps G prime H prime to G double prime H double prime. Also, the distance from H to B is 9, and the distance from D to H double prime is 4. So we knew H to B here is 9, D to H double prime is 4. Don't worry about these other two yet. So let's first deal with part A. Name any segments congruent to the following. So first off, any segments congruent to HG. So HG here would be congruent to H prime G prime, and it would be congruent to H double prime G double prime. So HG congruent to H prime G prime, and then congruent to H double prime G double prime. Segment HB. So HB right here would also be congruent to segment H prime B, because if we reflect H over B, then H prime to B has to be the same distance. And then GA. So GA down here would be congruent to G prime A for that same reason. If we reflected G over line K here at point A, then G prime to A has to be the same distance. In part B, does AC equal BD? So does the distance from A here to C here equal that distance of B to D? So yes, they are equal. That distance of AC equals BD, because we know that G double prime, that segment, G to G double prime here, and H to H double prime are perpendicular to lines K and M. So that means segment BD and segment AC are opposite sides of a rectangle. And those opposite sides of a rectangle have to be congruent. Then, part C. What is the length of segment G double prime? So the length from point G to point G double prime here after our two reflections. Well, what we know is this distance is 9, and this distance then is also 9 because of reflections. So if this distance is 4, that's also 4. So if we're using then theorem 9.5, the distance between G and G double prime would be the same as H to H double prime. Same distance because it's the same two reflections. So that would tell me that it's 2 times the distance between line K and line M. So that distance from point B here to D, which would be 9 plus 4, or 13. So the distance from point G to G double prime would be 2 times that distance, and 9 plus 4, 13 times 2 is 26 units. Then we get to our final theorem, which has to deal with theorem 9.6, reflections in intersecting lines. So if we're doing a composition of a reflection followed by a reflection, and it's over 2 lines that intersect at a single point, that also results in a single rotation from that original figure to final. So if AB is my original segment, and I reflect it over K, then over M, that would be the same result as simply taking segment AB and rotating it around point P to get our final segment. So let's look at the theorem. It says if lines K and M intersect at point P, then a reflection in K followed by a reflection in M is the same as a rotation about point P. Here's the key piece. The angle of rotation is represented by 2x, where x is the measure of the acute or right angle formed by lines K and M. So, our angle of rotation is 2 times the angle measure of the lines intersecting. So if line M here and K here intersect at x degrees, that final rotation from AB to A double prime B double prime is 2 times that measure. So if that was 30, our rotation would be 60. So our final example says in the diagram at the right, pre-image is reflected in line K, then in line M. Describe the single transformation that maps the blue figure onto the green. Well, we can't see the colors here because it printed black and white, but let's look at this. If this is our original pre-image, reflecting in line K, giving us this, then reflecting in line M, here would be our final image. Well, we know M and K intersect at 80 degrees. So from this figure to this figure, it could be described as the single transformation of a rotation of 160 degrees about point P. Because of theorem, right here, 9.6 telling us that the rotation angle measure is 2 times the measure of those intersecting lines.